Okay, so for today's lesson, again, something about rotated conic sections, but this time we're going to be learning how to discriminate from the general second degree equation. And the motivation for this one is that you might be solving one of these two problems. Problem number one, you have a second degree equation. Remember that a second degree equation is an equation that has only power, well, that the highest power that you see is the second degree power like this, something square, or like this, and you want to tell what it is. Remember that since you know that this is an equation of second degree, you know that it's going to be either a circle, a parabola, a hyperbola, or an ellipse. Or second problem, you're able to graph the equation, you see what it is, but you have identified it as a rotated conic section and want to tell what the rotation angle is. In this case, the equation that I'm putting as an example is a parabola, and you can see that the axis of the parabola is not looking in any of the direction of the regular axis. It's rotated, so you want to tell what's the angle that this parabola has been rotated to. Well, the solution for any of these problems is to look at the discriminant and identify some key elements. What's the discriminant? We're going to define it later on. In yesterday's equations, we were using only these forms. These forms are called standard equations. And these are useful because they include some parameters that you can see in the graph. So if you have the graph, you can identify these parameters and put them in the equation. And if you have the equation, you can immediately identify the parameters and put them in the graph. That's why these equations are useful. But imagine that we have something like this. This is clearly an ellipse, and we can develop all these things. If I wanted to simplify this equation, I would have to multiply by the least common multiple of these two, which is 36. So I multiply the left-hand side of the equation and the right-hand side of the equation by 36. This is what I get. Then I will have to develop these squares. After that, I would have to FOIL it. Remember, this by this, this by this, this by this, and so on. I obtain this. I'm going to put all the numbers here. So I'm passing the 9 here, and I'm moving the 36 to the left side. And then if I simplify this, I obtain this. Now, this equation and this equation are completely equivalent. This one is the standard equation, and this one is called equation in general form. Okay, so I've gone from standard equation to the equation in general form, and that is a pretty simple process. I just developed the squares, simplified a little bit. So remember the first problem? The first problem was that you had an equation in general form, like this one, and you wanted to identify it. So maybe you're thinking, well, if I could go in this direction, maybe I can go in the opposite direction, right? That is actually something we do, and the process in doing that is called completing the squares, but there are some times that you can't simply do that, or that it's really complicated, it's cumbersome, involves a lot of calculations. So what do you do? Well, instead, let's look at what's the form of the most general equation of second degree that you can think of. It includes a square term on x, a square term on y, linear term of x, linear term on y, a free number, and this one over here is called the mixed term. This mixed term is the one that is going to give you the rotation of your conic section. If this one exists, your conic section is a rotated one for sure. So in the example that we just obtained, this is the equation that we obtained, and we would just need to identify which are the coefficients in each case. So the coefficient of the square term on x is a, the coefficient of the linear term on x is d, the coefficient on the square term on y is c, the coefficient on the linear term on y is e, and the free number is f. We have identified that. Now what? Well, the discriminant by definition is just b squared minus 4ac, and well, calculate it, because if you calculate it you can tell immediately what type of conic you have. If the discriminant is less than 0, it's a negative number, you have a circle or an ellipse. You only have a circle if a and c, if the coefficients for the squared terms on x and y are the same. If they are not the same, then you have an ellipse. If the discriminant is 0, you have a parabola, and if the discriminant is positive, you have a hyperbola. Okay, so it's really just that simple. You don't even have to know what number you have, and it doesn't really matter. What we're just looking at is the signs, basically. Negative sign, positive sign, 0. With that we can tell whether the function is a circle, an ellipse, a parabola, or a hyperbola. Back to the example. We have identified these ones. Plug them in here. There is no b, so this one's 0. Minus 4, a is 9, c is 4. Compute this, negative 36. This is clearly less than 0. And remember that less than 0 meant either circle or ellipse. But since a and c are not the same, this is an ellipse, as we already knew. Second example. Imagine that you have this thing. In this case, we do have all the coefficients, a, b, c, d, e, f. And we have a mixed term here, so we know that this is a rotated conic section. What is the discriminant? Well, again, plug in the b, plug in the a, plug in the c, compute. This is equal to 0. Remember what it was? Equal to 0 meant that we had a parabola, so this thing is actually a parabola. See, it's just that easy. Now, try it for yourself.